Okay.
Okay, so thanks everybody for coming to this second lecture, again by Luigi, who will continue talking about localization. And today is part 2 about supersymmetric theories in 3 dimensions. So thanks again, Luigi. The stage is yours.
Okay, thank you again for the introduction and thank you all for coming. Now I share my screen. Okay. So do you see my screen?
Yes, great.
Perfect. So I can start. And before moving to the three-dimensional theories, let me add something that I forgot to mention yesterday. And there's another reason why. So I mentioned that there are several supersymmetric backgrounds that one might consider. And there's of course, there's another reason why we are interested in it. This because, and the reason is that different backgrounds can lead to different observables. So today I will discuss the background on S3, but there's also, for instance, the background on S2 times S1, which is related to different types of indices, supersymmetric indices. But there's also for the squashed sphere, which allow through some specific derivative to obtain information on the correlator of the stress tensor in supersymmetric theory. So it's not just an exercise. There are very physical motivation to explore different backgrounds. So okay, now we can what I'm going to do today is to write to apply localization in three-dimensional theory in S3 and derive some matrix model from localization. So let me start setting some convention for the three-dimensional theory. So we work in three-dimensional n equal to supersymmetric theory. We are in Euclidean signature. And for now, we limit to flat space. We need I need some spinor lambda with a index with a spinorial index alpha. It's a Dirac spinor. Alpha runs from 1 to 2 and is a spin free, which means an SU2 index. So these index are raised and lowered by the epsilon, which in my convention is this. And there's also the gammas, like for algebra, which are just the Pauli matrices. So they satisfy this relation, which we all know, but let me write it. And finally, when I write to spinors, the contraction is always in this way. And if there's a gamma, this is the contraction. Okay, I want to write Lagrangians which are invariant under the n equal to superalgebra, which has this form. So my superchargers Q and Q tilde, and they satisfy this relation. So B mu is the generator of the translation. Then there might be a central extension, QQ, and Q tilde anti-commute, and also Q alpha with P mu and Q tilde with P mu commute. So this is the abstract n equal to algebra. So now it's time to write some Lagrangian. And if you want in three-dimensional n equal to theories, we have a superspace construction, but which is, okay, three-dimensional n equal 2 is just the dimensional reduction on for the n equals 1. That's why we have a superspace. And so I can just adapt what we know from for the n equals 1 to this case. So my relevant multiplet will be a chiral multiplet. So phi will be something like this. It will be a scalar field phi, a Dirac fermion, and an auxiliary field. Then there's the vector multiplet, which contains a vector, a scalar, which, if you want, is present, can be understood from the fact that when I reduce the four-dimensional n equal 1, the fourth component of mu becomes this scalar. And then I have two gauginos and an auxiliary field. So the Lagrangian I can write is for sure the superior Mills Lagrangian, which in some convention is looks like this. Then I can write the Lagrangian also for the matter, including the interaction with the gauge group. So here the chiral field lives in some representation of the gauge group, and this is the Lagrangian. Minus. And then they have the auxiliary field. So these actually they come from superspace construction. So this theory are invariant under some supersymmetry transformation generated by an operator delta, which is defined in this way. Epsilon and epsilon tilde are my supersymmetry parameters. Let me write let me write the transformation for the vector field. So notice that this transformation for the gaugino lambda will depend only on epsilon. Then I have a similar one for lambda tilde. It's not exactly the same. There's a here there's a minus sign. Here there's a plus. And this depends only on epsilon tilde. And finally I have delta D, which is like this. Okay. So if you want, as an exercise, you can compute maybe the simplest one is delta square on sigma, and you see that this is something like E epsilon tilde gamma mu epsilon d mu sigma. So it's something like E v mu d mu sigma plus some gauge transformation on sigma. So this is the, if you can think to this as the derivative of dig on sigma, and the gauge transformation should be the contraction of V with the gauge field. Well, I'm not sure about the I, so let me. And if you, well, you don't see this term here, but if you compute other delta square, you can derive that there's also this scalar here in the gauge transformation. So this essentially this gauge transformation from a superfield perspective can be understood from the fact that you have to restore the West Zumino gauge, if you are familiar with superspace. Okay, but we are in 3 dimension, and we know that this is not the end of the story for the action we can write. And in fact, there's also the famous Chern-Simons action, which is in the non-supersymmetric case, it's like this. So it is, as you probably know, it's topological. And for instance, it can be written as A wedge dA plus 2A cube. So at least at the classical level, it doesn't involve the metric. At the quantum level, the story becomes more involved, but I don't want to enter in this. This action is not gauge invariant. But it turns out that if you consider the exponential and you perform a gauge transformation, this will change something like e to the ik times some factor, which is an integer. So if you choose k to be an integer, the theory is gauge invariant, and it's fine. So yeah, actually, this is the quantization condition for the Chern-Simons level. Oh yes, case is called Chern-Simons level, and this is strictly, this quantization condition is strictly true for probably UN, and if the trace in the fundamental. But this is the case I will consider when I write a specific example. So we are fine with this. Now the question is, can we make this action supersymmetric? And the answer is positive, otherwise I wouldn't have mentioned this. So you can, if you want to derive the supersymmetric version, it's you can do the exercise of varying this action with the transformation I wrote above, and with some work, but it's something reasonable. You can see that there is the action admits a supersymmetric completion, and we can write the supersymmetric action. So there's the standard Chern-Simons. And then there are two contributions. So you can, from dimensional analysis, you can also imagine that these are the only two terms that can appear, and the question is which coefficient I have to put in front of them to make it supersymmetric. Here there's a parenthesis, and notice that d, sigma, lambda tilde, and lambda are auxiliary fields in this theory. So if you give me the supersymmetric theory and the non-supersymmetric theory, the result, if there's no matter, will be the same. Okay, now we have to write this theory on S3. So I need to set some convention for S3 for my manifold. We need to, since we have spinor, we need to introduce some orthonormal frame or a Feldman. So an object which carries so now the Greek indices become the vector indices on S3. The Latin indices are flat space indices. So their Feldman is defined by this condition. Then I can define my spin connection. And if there's no torsion, the equation that fixes the spin connection is the zero torsion condition. Treat it like this. So a spinor is an object which is in a way charged under the Lorentz rotation of the Latin indices. So I can use the spin connection to define the Scoria-Varian derivative. Like this. And yeah, I want gamma with the Latin indices are the Pauli matrices in 3 dimensions, or the standard clip for algebra, but it's usually more convenient to work with the Clifford algebra with I don't know if it's a Clifford algebra with some gammas with Greek indices defined in this way, and because it satisfies this condition. So on S3, we'll have free coordinates theta, phi, and tau. Theta is a compact coordinate. Phi and tau are two circular coordinates. These are called sometimes toroidal coordinates. And the reason is that if I use the standard matrix, this is something like this. So for a fixed value of theta, this is a torus. That's why it's called. They are called toroidal coordinates. Now I have to choose my frame, but S3 is a rather special sphere. It's also a group, Ali group. So can choose a very nice frame, which is the left invariant frame, which is related to the Maurer-Cartan form. And so it satisfies the Maurer-Cartan equation, which if you compare with this equation, you can with this equation here and the Maurer-Cartan equation, you get the spin connection is proportional to the Firbein. And from this, you get the covariant derivative on the spinor like this. Okay. I think I defined everything I need. Now it's time to start to modify our SUSY supersymmetric Lagrangians and supersymmetry algebra. So I will, even though yesterday I said that the method of coupling the theory to supergravity is more convenient, I prefer to apply the first method because it's more straightforward. I will eventually I will make some comment and to make contact with the two methods, but I don't want to enter in the various supergravity backgrounds field. So I think it's also useful to, because there are some cases where you just want to apply this method. So I will do for the vector multiplet. So a good starting point is to write the dimension of my fields and see how can I do for the SUSY algebra. So these are the dimension of the fields. A and sigma have dimension 1, the gauginos have dimension 3/2, and D has dimension 2. Then I know that my Q has dimension 1/2, and that delta has dimension 0. So I want epsilon with dimension minus a half. And so you remember that delta a mu flat were something like this. I'm not sure I'm putting the correct sign here. Okay, so it's if you try to build something else with so which term you can imagine to include something that is proportional to the covariant derivative of the spinor. But this is as dimension a half, and so you cannot really write anything for delta mu, and also for delta sigma is just delta sigma flat. Instead, for the gaugino, we can do something. So here. Oh, sorry, gamma mu nu is defined as a half the commutator of the gamma. Here, my left-hand side has dimension 3/2, so I want to write something with d mu epsilon, and I'm making the ansatz that nothing will depend. The variation of lambda won't depend on epsilon tilde. So here I have a mu, so I contract with gamma. And this has dimension a half, so here I can add sigma and I put a coefficient in front. From delta lambda tilde, the story is similar. So this will be delta lambda flat. Well, here with flat I mean also minimally coupled, but and you can add a very similar term. And with similar consideration, you can also write a term for delta d in this way, where I'm making also here some ansatz on based on the form of the flat space supersymmetry. So if you are okay with this, I can start looking at the closure of my supersymmetry algebra. And this I want something that is reasonable. So if I do this exercise for all the fields in my vector multiplet. So for a mu, you might want to find something that will be a Lie derivative along V, plus what you can admit is a gauge transformation. So here you see you vary the first time A, you get the spinor, then you vary the spinor, and you get something that will contain A1 and A2. And so you can use this condition to fix A1 and A2. Then you do the same exercise for lambda and lambda tilde. And this commutator will involve the variation of this, so you can fix also A3. And A3 turns now to be equal 1/3. Now you finally do for D, and you will get the derivative of D minus A lambda D. So now everything should be fixed. I don't apparently have no more freedom, so this should be already reasonable. Then I get something like this, which sounds like a dilatation generator. And then I find something which is which makes me very disappointing at first sight, which is a term proportional to sigma, which is not compatible with the supersymmetry algebra. But actually, I haven't specified anything about my spinors epsilon. And what you can impose is the Killing-Spinor equation for epsilon and epsilon tilde. So you can verify that using this, the ugly term vanishes. So this is, we don't, but, and also rho, which is, I can write rho for you, 1/3. So I'm using my Killing-Spinor equation, this is 0. So maybe I haven't stressed enough yesterday also this point. It's important that to apply localization, yes, it's important that delta squared is something which is a compact symmetry. So I don't think there's any theorem which says that delta square cannot be something which is non-compact, but as far as I know, there are many examples where if this is not T1, you will end with some troubles with the localization locus, but I don't think there's really a no-go theorem that says that it's non-compact, but they say that localization doesn't work if delta squared is non-compact, but it's nice that we don't have to discuss this problem because of this condition. Another thing is that using the Killing-Spinor equation, the vector v mu constructed in this way is actually killing. You can verify this. So now you have fixed your supersymmetry algebra. Now you should impose that yes, that your actions are invariant under the supersymmetry transformation. And so you might expect that, for instance, in Mills, you could have terms like this. Terms like this. And like this. Sorry, this is. Now let me call the radius of the sphere L, sorry. Okay, so these are the kinds of terms that can appear, and now it's that it's up to you to choose what you can add or not. And after some boring computation, you can fix everything. And the Super-Mills Lagrangian on S3 is reads like this. Another good reason why you don't want the dilatation generator is that the Super-Mills Lagrangian is not scale invariant. So if you have a dilatation in your supersymmetry algebra, probably you are not able to write a supersymmetric Mills action. So you see that there are this term proportional to 1 over L, which are which appears and vanishes eventually when L goes to infinity. Okay, I can actually wonder about the super Chern-Simons action, but here life is easier because since this action is conformal invariant and S3 is conformal equivalent to S3 to R3, you might imagine that nothing changes, as in fact nothing changes. So the Chern-Simons action is what you expect. Let me rewrite for you. Okay, now in principle, I have to do the same thing for the matter action, but the story goes along the same line, so I will skip it and I give you the answer. And actually, I can be a little bit more general, and I write the action for a chiral field with a charge R. So phi as R charge R, and the matter action is this one. know that this is boring, but it's an important part. Finally, I have also some interaction with the gauge field. Okay, so here you have an explicit dependence on R, and also you have some term which has the 1/L coefficient. So for the chiral, the Susy transformation are like this. Okay, almost done. And the Susy algebra confides in some convention, should be like this. So there's also this term proportional to their charge. Of course, here you see that you get this. It's something reasonable, but you don't know how these appear. Instead, if we, from a supergravity point of view, if we use the supergravity point of view, we would have understood better. So before a break, like the last 3 minutes, I just want to say something on this. So since we are interested in theory preserving our symmetry, if you want to couple supergravity, you can take the R multiplet. You can take the stress tensor living in the R multiplet, which is a way to say that this the multiplet T will contain T mu nu and an R symmetric R and then other fields. Then you couple to gravity, as say yesterday, and I just want to write the generalized Killing-Spinor equation and see that. So the supergravity multiplet will contain G mu nu, another symmetry gauge field which couple to J mu R, the gravitini, and other stuff. So if you apply, if you write everything correctly, at the end of the day, you arrive to the generalized Killing-Spinor equation, which are something like this. And then there are, I'm using a lot of those, but the reason why I'm using that is because they will be zero on the S3. So now you can choose your metric to be as free. And you see that if you choose a mu r to be 0 and h to be minus I over L, you recover the Killing-Spinor equation that we obtained imposing the closure of our algebra. However, from this equation, we have all the other bosonic fields, and so you can build all the backgrounds that I mentioned as 2 times S1, the square sphere, and you can maybe also some thing more general. There's a series of paper by Festuccia, Komargowski, Closet, and Dumitrescu, which deal with this in many details. And and then you look at your algebra, and you find that this will contain the Lie derivative with respect to V, but also something like this. So if which agrees with what I wrote above. So this term is actually due to the presence of these background fields in your supergravity multiplet. Okay, I think we can have a break now, and in the last part we will do the actual localization computations.
Okay, great. Thanks, Luigi. So if there are questions, comments, please just unmute yourself and ask. Okay, I think we can resume in 5-8 minutes.
Yeah.
Okay, next. Okay, pay attention that you are muted. Okay.
Okay. Okay. Yes, I'm here.
We can resume.
Okay. Here we are.
Yeah, it's working.
Okay. So is there any question? Okay, I can go on. So now it's time for localization. So the first thing to do is choosing our localizing supercharge. And we, sorry, just. So the left invariant frame that I chosen is particularly nice because Killing-Spinor here are very simple, because the mu epsilon is reached like this, and so these are just constant spinor. So I choose epsilon to be 1, 0, and epsilon tilde to be 0, 1. And so this is my localizing supercharge, and you can verify that the vector v. So the geometry that is generating this supercharge is something that is proportional to d tau plus d phi. And if I'm chip points along an off fiber. can see you can see it better in another set of coordinates, but okay. And so my delta square is given by this isometry. Then there's an Arsenic transformation and the gauge transformation G lambda, where lambda is again EVA plus epsilon epsilon sigma up to some I. Now I should write the localizing term, but it turns out after some long and tedious computation that the Super-Yang-Mills action is Q exact. It's an exact variation. This is and also the matter action is exact. And you can wonder if every action is exact, but fortunately the Chern-Simons action is not. So my partition function can depend on the Chern-Simons level. And in any case, my localizing terms are the Super-Yang-Mills action and the matter action. Okay, let's start with the gauge sector. As someone of you pointed out yesterday, we have to perform the gauge fixing because we are quantizing a gauge theory. So my gauge condition is this one. And I need to add the corresponding ghost action. So now there's a subtlety, which is the fact that I should write an exact term for a delta prime, which is the sum over my supersymmetry variation and my BRST variation. But in this case is not a real problem because I can choose a W prime, which is the one I use for Super-Yang-Mills, and the standard BRST term. And so when delta, this is will give you just as Yang-Mills, Super-Yang-Mills plus the ghost action. And the reason is that when delta, then when the BRST variation, it's the Super-Yang-Mills term is gives 0 because it's BRST invariant. The only problem might arise when delta it's the usual is the other part because there's a mu. So the only problem could come from a term like this. But I need this start to compute one loop determinants. And this is something like C bar lambda, will give some interaction C bar lambda, C lambda tilde. And if you think in a Feynman rule in coming from this interaction, it never enters. It can't enter in the one loop in any one loop determinant. So we can safely ignore this term. So essentially, I don't need to worry about the fact that I should consider this delta prime, and I can go on safely. Now I have to determine the localization locus. So here I choose my contour integration, and the choice is such that this is positive definite. So a mu sigma will be real, maybe also D. No, well, this I'm not sure that is real, but a mu and sigma must be real. And lambda tilde should be equal to lambda W. Well, let me put quotation marks, but I want the condition that makes my path integral positive definite, my superior Mills action positive definite. So in this way, the bosonic part of superior Mills is the sum of squared. So I have the F mu squared, d mu sigma squared, and d plus I sigma over L squared. So the locus is determined by the equation F mu nu equals 0, d mu sigma equals 0, and d equals minus I sigma over L. Okay, so F mu nu equals 0 implies that the connection are flat, but on S3 the only flat connection is A mu equals 0. If you want, the reason is that S3 is simply connected. So if I have a flat connection, I can always, the corresponding alarming can always reduce to a point. And so at the end of the day, they are all equivalent to A mu equals 0. So I simplify the second equation to d mu sigma equals 0. So sigma is a constant. And let me call sigma 0 over L. And this becomes sigma 0 over L squared. Then you should look at your fermionic part of the Mills action. And it will contain something like this, but there's also something like this. So I don't. So you see that there are no fermionic 0 modes. And so my solution is lambda equals 0 and lambda tilde equals 0. So if this is clear, I can now expand my Mills action at the quadratic order around the locus. So every field will be alpha 0 plus 1 over square root of t phi prime. So I denote with the prime the fluctuation. And that's prime. Yeah, means which is my superior means which is my action expanded is with the t in front. Should be something like this. Minus 1 over 12 mu sigma 0 squared minus a half d prime plus I over L sigma prime squared lambda prime d slash lambda minus 1 over 12 lambda prime lambda. Then there's also here a lambda. Okay, this is then there are might be some leading term in 1 over t, but it doesn't matter because I'm taking the limit t to infinity. So f prime mu nu is abelianized. So it's only this term that enter. So to compute the determinant is useful to further decompose a prime in a divergence-less vector plus a pure divergence term. This is, I think it's some old decomposition, and B mu satisfies this condition of being divergence-less. Now, actually, there's room to implement a further gauge transformation. So I can, so up to now, sigma is in my Lie algebra of the gauge group. But with a gauge transformation, I can, sorry, sigma 0. I can reduce sigma to live in the Cartan of my Lie algebra. And remember, please, that the Presto is van der Monde, I don't know the spelling, so our determinant, which is a van der Monde determinant. And I will add this, I will at the very end of the computation. But if you want, this is can be obtained performing the standard for the Popov gauge fixing. But so since sigma 0 is in now is in the Cartan, I can, so this is expansion 1, this is 0.2, and then there's 0.3. I want to expand my fields in a Cartan basis, so there will be a term with F0. So F denotes a generic field. So I decompose in Cartan plus root vector. So I will have this. My root vectors are normalized in this way. And the advantages is that sigma 0 F0 commutes by definition, and the action of the root on the Cartan gives the roots. Okay.
Sorry, can I ask a question? Sorry.
Yes, sure.
Yeah, I'm a bit confused by because previously you fixed the gauge by imposing that A mu is divergenceless, right? But now you seem to impose another gauge condition where sigma is diagonal.
You can do. Yes, I'm doing this, but you can do this because sigma 0 is constant on the locus. So I'm not imposing that the fluctuation of sigma
Okay.
only the constant part sigma 0.
Okay. So this is fixing the constant part of the gauge transformation. Okay.
Yeah, exactly.
Okay. Thanks.
Thank you for the question. Okay. So now I want to, there are some path integrals that are easy to perform, and I will do so. I have a prime mu, which becomes db mu d phi, where phi is this scalar appearing in my decomposition. And so why I want to perform the integral over phi, the integral over b, which is in the ghost action, the integral over the ghost, and the integral over the fluctuation sigma prime and d. Okay, this is a little bit ambiguous, but so I start with integrating out, and I want to use the ghost, the action for sigma prime, and d, and eventually phi. Okay, so the d is easy to integrate because it's just an auxiliary field. Then I integrate out b, which imposes delta d mu a mu equals 0, a prime mu, sorry, because I'm also expanding my ghost action. But this, if you remember my decomposition, this gives just the condition that del square phi is the delta of the del square phi, which I can write as delta of phi over the square root of the determinant of this operator del square. So I can have integrated out b. Now I can use the delta to integrate out the field phi. The ghost action is free and it involves only this, again, this operator del square, but so here let me put an equal. It will give me a contribution at the numerator. Then I have to add this square root of del square. And finally, so I'm integrating out the ghost, but then I have to integrate out over sigma prime. And so here I got another, this sigma prime, you can check that is free and gives this determinant, and so they cancel. So at the end of the day, I'm left only with the integral, of b mu and lambda, which and actually I'm interested only in the part that couples to sigma 0. So at the end of the day, I want to compute the determinant that arising from this. So after some computation, you can get this. Not to write in this line. So I'm neglecting the Cartan part of B mu because it doesn't depend on sigma 0. And alpha 0 is a shorthand notation for alpha of sigma 0. Same story for Guerrini. Okay, from this expression, you can formally write your determinant like this. There will be a product over the roots, and there will be determinant of the Dirac operator plus 1 over alpha 0 minus 1 over 12 over the determinant of the Laplacian coupled to alpha 0 squared, and this determinant is computed on divergenceless vector on S3. Now there are various ways to compute this guy, but I will, since we are on S3, which is also a group manifold, it's particularly nice, and all the modes are known, so we can just put the eigenvalues. In more complicated cases, you might need more refined argument, but here we can just expand the mode, put the all eigenvalues, and so let me try to make a table with the eigenvalues and the degeneracies. We put the eigenvalues, here the degeneracy. Scalars, actually, the eigenvalues. So you can label with the eigenvalues with some integer j. Sorry, j is not integer because it's only positive. And so if you would like to derive, you can try to exploit the fact that the isometry group of S3 is SU2 times SU2. So if you are able to express these differential operators in terms of angular moment of SU2 left and SU2 right, you can derive all these property. You can find more details on these, for instance, in the review by Marigno. So this is a divergenceless vector. So you plug in this result in your one loop determinant. You will find an horrible product. Okay, I'll write this time. Horrible infinite product. But is so horrible because I'm doing a computation that is not optimized, in the sense that many of these modes that I'm considering are actually coupled by supersymmetry. So after some steps, which basically are clever definition of J, you can simplify this product a lot, and you arrive to something like this. J plus 1, J minus 1. Now you exploit the property that if alpha is a root, also minus alpha is a root. So you can restrict the product over positive root, product of J, and this become J minus I alpha 0, J minus alpha 0, the J plus 1. And so you are left with the product over the positive roots of J squared plus alpha 0 squared. And now you can, if you factor a J to the fourth term, which is your divergent part, which can be regularized, for instance, uses the zeta function. You get something like this squared. And after the zeta function regularization, you get the answer. So here you recognize sinh of x over of alpha 0 over pi alpha 0. And so at the end of the day, my one loop determinant is this. So the hardest part is over. Now I have to evaluate the classical contribution from the Chern-Simons action. So all the fields are 0 apart from D and sigma, so there's a contribution. I hope that I'm putting the I in the correct way. And so but sigma 0 is constant. And so this is proportional to the volume of, the integral is just the volume of S3. And if you combine everything, this is just the trace of sigma 0 squared. Now, the only very last thing is that in sigma 0 is in the Cartan, and the price to pay is this van der Monde determinant. So the determinant which is just the product of pi alpha 0, which simplifies maybe squared, which simplifies with the one loop determinant from the vector. And so that's why you always see that the vector determinant is the determinant over the adjoint of the hyperbolic sign. Maybe with that too. where with this notation, determinant in representation R of a function of sigma 0 is the product over the weights of the representation of F computed in the weights. So here the definition coincides. And essentially the matrix model for my Chern-Simons theory on S3 is this sigma 0. Then there's the classical contribution times this determinant. So without matter, all the extra field due to supersymmetry are auxiliary. So this result also for the non-supersymmetric case. So this, and it agrees with previous results. Now let me go quickly. Is there any question about the computation of this for the gauge sector? Okay. I can go briefly through the matter sector. So here my Lagrangian. I write the Lagrangian on the localization locus, which is also, so this is also my localizing term. So at the end of the day, I want to compute the determinant of this related to this term, plus 2 minus r phi, and there are the fermion minus I over L psi sigma 0 plus r minus a half psi and the auxiliary fields. So here there's no moduli, so which means that the localization locus is just phi psi every fields to 0. So here I do the same steps as before, but instead of expanding over the roots, expanding over weight basis. And so just to write something. This is the product over the weight space of the representation R of my chirals, and the determinant I have to compute is this. So here we have more terms. Rho 0 is rho sigma 0. R 2 minus R. And so using the table I wrote before, you can compute the eigenvalues. There's again a lot of simplification. So let me write that you have to work to get this final expression. Plus 1 minus r, j minus I over 0, plus r minus 1. This is so this is the final form, because now I can relate this expression to a special function called double sign as b of x, which is can be written in this way. Where q is b plus 1 over b, but now if you set in this expression b equals to 1, you can see that this formula becomes much simpler, because essentially you have m plus 1 minus ix, m plus n plus 1 plus ix. So if you reorganize m and n in m plus n and m minus n, this is a sort of, if you implement this change of variables, and m plus n eventually becomes j, you see that this product depends only on j, but there's also some degeneracy due to the fact that it doesn't depend on m minus n. So you must wonder how many m plus n can I make varying m minus n, and the answer is again j, and so you can recover this expression here. So if you will get the functional determinant of this double sign at b equals 1 at the end of the day. So the chiral one loop is this, means SB double sign of b equals 1 or sigma 0. And so the matrix model for Chern-Simons theory, super Chern-Simons matter theory, is something like this. There's the Chern-Simons term, then there's one loop determinant for the vector, and then there's all the matter contributions. So how can I write the chiral I sigma 0. Okay, so which eventually they can have different charges, and you can start. So thanks to localization, we are able to reduce a rather intricate path integral to an integral over matrices, which is now that is much more simpler to study. Okay, let me just explain how to some particular case. So if this results also for theory which has at least n equals 2, but you might wonder if there's any simplification for higher supersymmetry, and the answer is positive. So if n is greater than 3, the matter is organized in hypermultiplets. So an hypermultiplet is given by 2 chirals of our charge equals a half and transforming in conjugate representation. So the one loop term for the hyper will be something SB plus rho 0. Then there's a minus, and there's an identity that of the double sign function that leads you to this, to a simple determinant, which is expressed in terms of the hyperbolic 1 over the hyperbolic cosine. So this is nice because it's easier to study a hyperbolic cosine than a special function. Another useful simplification which you want to know is that if your chiral has R charge 1 and the representation is the adjoint, the chiral, the one loop determinant is 1, and the reason is from, you can see from this, if I go back this and you put R equals 1, then you can use again that if rho 0 is alpha 0, you have that for every alpha 0 there's minus alpha 0, and so this the numerator and the denominator simplifies, and this product is 1. This is useful for the n equal 4 vector multiplet, which is equal an n equal 2 vector plus chiral. So I'm decomposing the n equal 4 vector from the point of view of the n equal supersymmetry. There's a chiral with R charge 1 transforming in the joint. So Z vec of n equal 4 is equal to the vector of n equal 2. Okay, some possible application that are, well, one of the main motivation for exploring this proper localization to supersymmetric theories was to compare with the ADS-CFT with the result of ADS-CFT. But in 3 dimensions, yeah, you can do this, and maybe I will say some words more, at least for one applications. But in 3 dimension, a very interesting quantity is also the free energy F, because it's sometimes it plays the role of the anomaly or the anomaly in 2 and 5 dimensions. So there's a depth maximization, depth theorem you can study with, at least in the supersymmetric case. Moreover, in 3 dimensions, there are many dualities like mirror symmetry, cyber dualities, and they can be proved using easily using this matrix model technique. And another interesting application is study loop observables like Wilson loop, vortex loop, or mixed combination of them. And something that I mentioned yesterday is this topological sector, which actually requires a different prescription to localize, but it has been found recently, and it has been used to fix many CFT parameters, which, for instance, can be used to fix some subleading term in the supergravity action in the dual theory. Okay, let me end this lecture by writing at least one explicit matrix model. And what I want to write is the Abjm matrix model. Which, so deriving the Abjm matrix model was the original motivation for developing this localization procedure. So, and the reason is that Abjm is famously dual to M theory according to the DS4 CF3 correspondence. So what is Abjm? It's an n=6 supersymmetric Chern-Simons matter theory. So here, super Chern-Simons. The gauge groups is UN. Well, let me put them in parentheses. If there's a them, the groups are equal, but they can also be different. Okay, and this theory has two Chern-Simons terms, one for the UN and the other one for the other UN, with opposite Chern-Simons level K. There's matter in the bifundamental. I don't want to describe in details the model, and there's also superpotential, which actually is what makes this theory highly supersymmetric. And this is more precisely due to M theory on ADS4 times S7 mod ZK. So if I want to write the Abjm matrix model, I need to decompose precisely my field content in n equal to language, and I have two vector fields. Then I have two bifundamental chirals and two anti-bifundamental chirals. The superpotential is something that I haven't discussed, but you can show in general that is superpotential is Q exact, and so it doesn't contribute to the matrix model. To write the matrix, so if I want to write the matrix model, I have to write the action explicitly, the roots and the weights explicitly. So for UN, this is the roots. Then, so with sigma, I denote the first UN. Sigma et is the second UN. Then you need to write the weights for the bifundamental. So sigma is diagonal. the diagonal matrix sigma 1 sigma n. Okay. So the bifundamental weights are just this. And for the anti-bifundamental, they are just this. So now I can put all the pieces together. So I have the integral over this sigma 1 sigma n sigma at 1 sigma at n. Then there's the classical contribution from Chern-Simons, which I can write explicitly in this way. And then there are all the Maglio loops determinant. Which I can write rather explicitly. There's the product over J, and also here there's the simplification of the hyperbolic cosine. And so I'm left with this. So you can, from this actually you can study this matrix model, and the first great success was that F was observed to be proportional to n to the 3 alpha, which is a clear sign that of the duality with the n theories. This can be matched with the supergravity computation. So this is the last thing I want to tell, and I think it's also time to stop. So thank you. And if there's any question, don't hesitate to ask, even now or in the next days.
Okay, thanks, thanks Luigi. Just a second, that there is a question in the chat. Okay, I'm going to read the question. Usually, unless you know the exact superconformal R charge of the infrared conformal field theory, the R charge of the chirals are only defined up to mixing with the U1 flavor symmetries. Do we need to take this into account here? Thanks, Zero, for the question.
Okay, you're right. So for a BJM, the R charge is equal to half, so you are already at the fixed point, so you don't have to perform this. But in general, you have to account to keep into account this, and you should do the F maximization procedure. So you should add your trial R charge, considering the mixing of the. So essentially, the point is that if you have an R charge, you can always mix with a flavor symmetry. So you should keep this into account, doing the F maximizations, consider the mixing, and this mixing, and you maximize F to this with respect to some trial R charges. But this is another story. For a BJM, we are at the conformal fixed point, so we don't need to do this. Does it answer the question?
There is a reply. Is including trial R charts the same as adding SUSY backgrounds for background vector multiplets?
Can you read again?
Okay, sure. Is including trial R charts the same as adding SUSY backgrounds for background vector multiplets?
I think so. I'm not 100% sure, but I think so. I mean, the flavor symmetry corresponds to adding this background, so I think so. I mean, an asymmetry can be thought usually can be thought as a complex mass deformation. So I think you can see this charge as a complex mass deformation, yes. By the way, if you are interested in this topic, there's a nice review by Silvio Pufo, which should be discuss this point in more details.
Eventually, Luigi, if you remember the archive number, you can write it or you can give it to me and I write it on the chat if you want.
Okay, I think I can easily find. So if we go back at the first page, you should think this is a giant review by Peston, which include different contributions, and one of them concerned the F maximization. So it should be obtained from inside this, but I can update these slides and include a review. I think it's might be relevant as for people interested.
Okay, thanks, Luigi. I think I'm going to stop the recording. So if there are questions that do not want to be recorded, just please unmute yourself and ask.